Okay, everybody have their notebooks? Okay, we talked yesterday about factorizations, and I introduced these words yesterday actually to you. But just to review, the strings of factors of a number are called factorizations of that number. In problem 4.1, you saw that the longest possible factor string is 840, for 840, sorry, is made up of prime numbers. We call this string the prime factorization. The what?
The prime factorization.
Good. In fact, the longest factor string for any whole number is the prime factorization. Why is that? I want everybody to think about that for a moment. Why is the longest string for any whole number going to be the prime factorization? Everybody just kind of thinking about it for a moment? Okay, explain it to the person next to you. Ready to go.
Okay. Well, this will do, Devin. Okay, so it's like the, what was the question? I have short-term memory loss. What was your question?
Why will the longest factor string for any whole number be its prime factorization?
Oh.
All right, what do you think?
Oh.
Ideas? Thoughts? Good, great.
Because it keeps going until it can't divide anymore.
It keeps going until it can't divide anymore. Something to add to that, Emma.
That was mine.
Okay, something to add to that.
Well, because every number or every string can end in
Okay, yeah. Once we get down to the prime numbers, we can't go any longer, can we? And every number is going to be eventually able to be broken down into a string of prime numbers. And that is our prime factorization. When we look at the prime factorization of a number, it sometimes helps us to have a list of prime numbers handy. Now, most of you are getting pretty good at figuring out whether a number is prime or composite. So if you want to do this, you can do this when you go into the problem. But you may want to make a list of the prime factors, or the prime numbers, from 1 to 30. All right, now today we're going to go to some more efficient strategies for finding the prime factorization. Yesterday, we just basically kind of kept trying and maybe seeing if we could get a longer string. Today, we're actually going to learn a method. We're going to learn two methods, actually, that you can use in order to find the prime factorization. Now, why do I say the prime factorization instead of a prime factorization?
Because B is the answer? B is more definite than A. Yeah.
Okay, yeah. When I say the, I mean that it's the only one, right?
A is like
A could be any one of them, right? You could have multiple of them. Do we have, would we say, a factor pair?
No.
Yeah, we would. Because most numbers have more than one factor pair, unless they're prime, right? Okay, but for the prime factorization, we just say the prime factorization because it's the only one. So we have two methods here. The first one is a division problem. And they've got an upside down one. You can also do it right side up if it works more easily for you. So for instance, if we're finding the prime factors of 100, we're going to put 100 in here. And then we're going to divide it by a prime number. In this case, they chose to do 2. So 100 divided by 2 is 50. Now we're going to take that number. If this number isn't prime, then we're going to keep going. What is a prime number that we can divide 50 by?
5.
Okay, we can divide it by 5. 50 divided by 5 is?
10.
10. Are we down to prime numbers yet?
Nope.
Okay, then we have to keep going. What can we divide it by?
Just 2.
You can just set it on that desk there. Just right there on the desk.
2.
Yes.
2.
Okay, we can divide it by 2. And what do we end up with?
5.
Do we have to keep going?
No.
No. So this is our prime factorization, right here. 2 times 5 times 2 times 5.
Wait.
Yes.
On that they did 2 times 2 times 5. We did 2 times 5 times 2.
Doesn't matter what order we do it in? Nope. It's a multiplication problem, so we can go in any order, and it still is going to make the same number.
Yes. The same numbers.
Yeah.
Just in different ways.
It's always going to be the same numbers, isn't it? And even though we went from 100 to 50 to 10 to 5, and they did 100 to 50 to 25 to 5,
still got the same answer.
We still got the same factors. And you're always going to get the same factors. There's only one prime factorization for each given number. Okay? So this is one method. Our second method is using what we call a factor tree. Everybody say factor tree. Now a factor tree is based on the same basic principles, but instead of just dividing by prime numbers, we can kind of divide by whatever numbers we want. Okay? So if we've got 100, we're going to find a factor pair that we can multiply together to get 100. 2 times
50.
2 times 50. All right. Now, any of them that are prime, we can circle those, and we know that that's going to be part of our prime factorization. Okay. And then for 50, what can we multiply together to get 50?
25.
Yes.
25 and 2.
Okay. We can do 25 and 2. Okay. Are there any of them that we're done with?
No.
Any of those prime?
Nope.
Oh, yes.
2 is prime, isn't it? So, we have to keep going on 25 though, don't we? Okay, and what are we going to do?
5 times 5.
5 times 5.
That's pretty cool.
And now, we've got our prime factorization.
Yay!
Now, what if we had decided instead of doing 2 times 50, what if we had decided to do 4 times 25? Would it work?
Wouldn't it give you? Yeah.
Yes.
No. Yeah.
No.
Well, let's see.
Yes, no.
Okay,
maybe
is
so.
4 prime?
No.
No, so that means we need to keep going. And what are we going to end up with?
2 times 2.
2 times 2. Is 25 prime?
No.
Nope, so we got to keep going.
5 times 5.
5 times 5, and what did we end up with?
2 times 2 times 5 times 5.
And how does that relate to what we came up with over here?
Same.
It's exactly the same, it's just in a different order, isn't it? We could also have gone for 100. We could have used 10 times 10.
Woo!
And then broken this down into
5 times 2.
2 times 5 and 2 times 5. Do we still end up with the same numbers?
Yes.
Yep, doesn't matter which ones we choose, as long as the numbers right here are factors, are a factor pair for the number above it, then it works. One caution that I'd like to give you for this is there are some people that they'll get doing this and they'll kind of lose track of what they're doing. And they might look at this and say, let's say for instance, right here, they might say instead of 2 times 5, they might say, oh, that is 7 plus 3. Is that a correct way of doing that?
No.
No, we're not adding here, are we? We're multiplying. So you can always double check by multiplying these two numbers together, and if it equals the one above it, then you're right. This would be a factorization for what number?
21.
For 21. Okay? So, just watch out for that. A lot of kids tend to make that mistake. Today, as you go into your... Oh, one other thing I need to talk about, actually. Exponents. Exponents are amazing. They help us to make it a little easier to write these prime factorizations. And basically what we do with exponents is if there is a number that we're multiplying in there more than once, like for instance in our 100, we had to multiply in there 2 2s and 2 5s, right? Instead of writing that as 5 times 5 times 2 times 2, we can change this into an exponent. Everybody say exponent.
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 An exponent
Squared and 2
is like squared and cubed and so on. Okay? So if we've got 2 of these, then we're going to change that into 5 squared.
Yeah.
And then we're going to multiply it by
2 squared.
2 squared. Now what if I had, let's do, okay, how would I write that in exponents? Yes.
Oh, one of the, take out one of the 3's.
Okay.
3 times 3 and put one of them squared. Wouldn't you put 3 at the top right?
What are we going to put up here?
I think of 3.
Yes.
3 cubed.
Nope, it's not 3 cubed. How many of them are there?
3 to the 4th power.
3 to the 4th power.
What?
The number that goes up here is how many times you're multiplying it by itself.
Oh, okay.
Okay, so since we're multiplying 3 times 3 times 3 times 3, that's 3 to the 4th power. The number that we're multiplying goes down here, and the number of times we're multiplying it by itself goes up there. Make sense?
See the 4.
That's okay. And then what's the other part of this going to be? Yes?
5, 3.
Okay.
5 cubed.
5 to the 3rd power, or sometimes we say that 5 cubed.
Why is it called 5 to the 3rd power?
We call this a power right here.
Yeah.
Okay, so this is to the 4th power, this is to the 3rd power.
Oh.
It's just the way that we name it. Okay? We could say, like, even if we've got, like, 5 squared, we could say that as 5 to the 2nd power, but usually people just call it 5 squared.
It's simpler.
All right, what questions can I answer about exponents and about efficient strategies for finding prime factorization? All right, if there are no questions, then go ahead and get started on problem 4.2. When you're done with that, you're welcome to do your projects or work on the homework. All right. It's up on the board.